Dijkstra's algorithm gives a way to find a shortest path tree, that is, a shortest path from a single starting vertex to all other vertices. It uses a greedy approach, building a cloud of vertices for which this shortest path tree has been obtained, and incrementally adds to it a vertex with the smallest distance label. When a vertex u is added to the cloud, all edges incident on u are relaxed. This edge relaxation step can update the distance labels for vertices adjacent to u based on whether a path traveling through vertex u gives a shorter path to an adjacent vertex. So when an edge from u to z is relaxed, when vertex u is added to the cloud next, we update z's distance label to be the better of two options, either whatever we had already before to vertex z, or we may find a shorter path going through vertex u, and the length of that path would be whatever u's distance label is. This is the distance from our starting vertex to u, plus now the weight of this edge from u to z. Now that you've seen an example of how Dijkstra's algorithm would work on some input graph, let's analyze the pseudocode to see how it's implemented, how efficient it is, and formally prove that it will correctly produce a shortest path tree. So given a graph G that has non-negative edge weights and some starting vertex S, so this is our single source, we want to find a shortest path from this single vertex to all other vertices. We're going to use a priority queue to keep track of the vertices that are not yet in the cloud. So this priority queue will use distance labels to keep track of the vertices that have the smaller distance label, that would be at the top of our minimum heap. We want to remove those vertices and place them into the cloud next. So first we have an initialization step. So just setting up the distance label for every vertex. So initially we set for the starting vertex, S, we'll set its distance label to be 0, and for everything else, its distance label is set to infinity, or integer max. Then every vertex is added to the priority queue, and its distance label is used as a key. Now additionally, when a vertex is added to this priority queue, we're going to keep track of where it is in the priority queue. You'll see why this is important in the last line. So because we update the distance labels for vertices later on when an edge is relaxed, we need a quick way to access where this vertex is in the priority queue so that when its distance label does change, we can shift it around in this min heap. So this just records where a vertex is in this priority queue so that later on, if we have to change the distance label for some vertex v, we know its locator. This is just a pointer to exactly where that vertex is in the minimum heap. Okay, so next step is to repeatedly remove vertices from this min heap. And we know that initially all vertices are in this priority queue. And we'll grab whichever one has the smallest distance label, and then relax all edges to that vertex. So remember that when we relax an edge, so this is going from some vertex u, which was just added to the cloud. This is mimicked by removing it from this priority queue. For this vertex u, and some edge e, which is incident on u. When we relax this, we update z's distance label to be the better of either whatever it was before. We can check to see what its distance label was before. Or we find a better way to get to z through u, and the length of that path would be however much it costs to get to u, plus now the cost of going from u to z. So this would be the new distance label of z. And we'll compare this to see if this is better than what we had already recorded. If it is, meaning we're going to update z's distance label, then we correctly set its new distance label to be that better one, that smaller one. And if we do this, we need to appropriately update the key corresponding to vertex z in the priority queue as well. Because now that its distance label has decreased, then it might belong somewhere else in the priority queue, now that it has a higher priority because it has a lower value in the min heap. So because of that, we'll find exactly where vertex z is in this priority queue and replace its key with this new value. So this might result in an upheap bubbling. So for example, this may be our min heap of vertices based on their distance label. And perhaps before vertex z was right here. So this represents the locator for vertex z. And when this distance label is updated and it decreases, maybe we have to shift z to go up to the root or to some vertex which is higher up in the tree. So this would be an upheap bubbling, or may result in an upheap bubbling. Okay, so how efficient is this really? Well, we know we go through this for loop n times because this is once for each vertex. And then what do we do inside of that? Just setting or getting a distance label is constant time. Setting a locator, this is just another label. We can do that in constant time. Now, this heap that we build up, we could use a bottom-up heap construction because we'll know initially all of the keys in advance. But just to show, for our heap, we know that this has n items in it initially because this is one for each vertex that we have. And if we just call insert into a priority queue implemented as a heap, each call to insert will be log of whatever the size of that priority queue is. So we'll have n calls to an operation which costs log n. So the number of iterations we have is n, but one call to this is log n. So far, the total running time for lines 2 through 8 is n times log n. Now let's look at the last few lines. We have a while loop, which goes through essentially each vertex in the graph, because we'll empty out this priority queue, which has all vertices in the graph, removing a vertex which has the smallest priority, the smallest distance label, and then we keep that vertex outside, we don't add it back to the heap. So again, we have n iterations. Let's put it this way. Big O of n iterations, exactly n iterations. And inside of this, we call this function remove min, so that we exactly remove that vertex that has the smallest distance label. But remember that this operation for a heap, just to call this one time, is log n. And then for every vertex that we have, we'll perform some operation, that edge relaxation step. So let's evaluate how efficient is this if we were to just call this once. Well, checking the opposite end of an edge is constant time. Performing this arithmetic expression is constant time because we can get or set labels in constant time also. So setting a distance label is constant time. And replacing a key, let's see what this is. So given a vertex z, we can immediately access where it is in the priority queue in constant time because we kept track of its locator. And we can update its key with a new, better distance label. But when we do that, we have to update in the priority queue, in the minimum heap, where that vertex z belongs because it may upheap. And when upheap occurs, since the height of a heap is no more than log n, then the number of swaps that would have to occur along an upwards path from vertex z to possibly all the way up to the root is no more than log n. So that's the number of swaps that we would have to make. But how many times do we call this function? Because just calling this once would be log n times. So the question becomes, how many times do we call this? This isn't once for every vertex, but for every vertex and every edge coming out of that vertex. In the worst case, we have to update the key every time. So how many total times do we execute this? Well, it depends on how many incident edges there are. Some vertices have more, some of them have less. But if we were to evaluate the total number of times for all edges that this gets called, well, this would be the sum of degrees. So for the first vertex, this will get called degree of however degree of that vertex times. And then for the second vertex, maybe it has more or less incident edges. and for the third one, and so forth, all the way up to however many vertices are in the graph. So the total number of times that these lines 12 through 17 are called is the sum of degrees of each vertex in the graph, which from the handshaking lemma we know to be 2 times m. So the total running time here we have for the first 8 lines, let me remove this, we have n iterations, and all operations here are constant time except for this one is log n time. So the total running time for them is n log n. Now for the next loop, we know we have n iterations of this, but a total of 2m iterations of lines 12 through 17 across all vertices. Total number of times we're going to execute those lines is 2m. And all operations here are constant time. Removing the min, this is log n. Replacing a key, because we have to do upheap bubbling, is log n. So our total cost here is big O of m log n, which means our running time for Dijkstra's algorithm is big O of n plus m times log n. Now sometimes you'll see that because we can assume that we're working already with a connected graph, meaning that there is a shortest path, there is some path that we can find from our starting vertex to everything else, then in a connected graph, m is big omega of n, which means that m is the dominant term here. So for those connected graphs, you may equivalently see this written as, for connected graphs, if we have an algorithm such as Dijkstra's, which runs in big O of n plus m, all of that times log n, then for connected graphs, this is the same as saying big O of m log n, just by dropping that lower order term n. If we have a connected graph, then that means we have sufficiently many edges that the number of edges m is big omega of n, that we have more edges than we do vertices. Okay, now let's see how we could also extend this a little bit, because right now this is just showing how we would record those distance labels. But what I had shown in the example was we do a little bit more than that, because we also record not only what is the length of a shortest path from this single starting vertex S to everyone else, but also what is the actual path which gave us that shortest length. And this can be accomplished by recording initially with every vertex a parent, so just another label, and then when a distance label is updated, recording which vertex gave a shorter path. So let me show you what that is here. Okay, so everything in red here, this is just what we had already with Dijkstra's algorithm, and then that text in blue are additions. So if we want to construct that entire tree and record the entire path, which was the shortest path, we can record with every vertex a parent vertex. So the only vertex which will not have a parent will be the starting vertex S. And for everyone else, this will be updated as we go along. We'll replace, when we update a distance label, then we'll replace whatever parent that vertex is with which edge we used, which actually gave that shortest path. So in this way we can recreate that path.